Hi everybody. Today I'd like to talk to you about how to code the magnetic field due to a moving charge in VPython. So this one is in response to a question in Matter and Interactions Chapter 17, Problem 60. And so in this problem, you've got a proton that's moving along the x-axis at 4 times 10 to the 4 meters per second in the plus x direction. In this little image at right, the proton is symbolized by the red sphere, and its velocity vector is the red vector. Now, the problem asks for the magnetic field at 4 positions in the YZ plane centered around the origin and at 8 times 10 to the minus 11 meters from the origin on the Y and the Z axes. So I'm going to show broken out how to do that for one position analytically and in code, and then I'll show you the code. So the position that it asks for is, or that I'm going to highlight, is the one in the plus y axis at 8 times 10 to the minus 11 meters, and its position is 0 on the x and the z axes. We're going to start the clock at t is equal to 0. I'm going to show you the analytical calculation for how to find it at t is equal to 0. In the code, I let the clock run, and I let the magnetic field evolve. Now here in this image, the kind of see-through sphere is the observation position. And I've shown a vector in cyan here that points from the position of the proton to the observation position. Now this is the vector r in the Biot-Savart law, right? Which is the displacement vector from the point from the current element or the charged position to the point of interest. So we are going to use the Biot-Savart law to calculate this. The Biot-Savart law contains a cross product. Now, I may have already told you this, but in case I didn't, to take the cross product of two vectors in VPython, you're going to use the command cross. And so it's just cross A comma B if you want to do A cross B. Of course, if you do cross B cross A, then that'll give you B cross A. Okay? So first vector first, second vector second. You put the two vectors inside parentheses with a comma in between them, and that's how VPython knows how to code it. Now I've got a link to my code shown here, and I'm going to go straight to it in the code. Remember that if we discussed lists in some previous lectures, you'll need to remember what you learned about lists in order to do this homework. So I'm going to show you in white what you would do analytically, and then in the green color what that looks like in the code. So here we have the Biot-Savart law. B is equal to mu naught over 4 pi. QV cross r hat over r squared. So this is the Biot-Savart law for a point charge. Now in this case, Q is the charge on a proton, which is 1.602 times 10 to the minus 19 coulombs. What I did in the code was I created a sphere object. It was a red sphere, as you saw, and I assigned it a new attribute called charge, or Q, okay? So here is the statement in VPython where I created the proton. So I made it a sphere. Proton equals a sphere. I gave it a radius. Now this isn't really the radius of a proton. That's much smaller, but I wanted you to be able to see it in the scale of the code. So I chose 1 times 10 to the minus 11. I gave it a position vector. That's the position attribute, pos, right? And that's the initial position of the proton. So that's its initial position vector. I made it red, and I gave it the charge attribute Q that contains the charge of a proton on it. I turned make trail on. Okay. Now, we also have to describe the velocity of the proton. That's the QV here, the V part. So mathematically, analytically, that would just be assigning the x-coordinate of a 3D vector as the speed. So that would be written as here. V is equal to 4 times 10 to the 4th meters per second, 0, 0. In the code, you just make a variable. You call it V. V is equal to the vector, and then 40,000, 0, 0, right? Now the observation points, that's the points where you want to know the magnetic field. I made those arrows and I called them all pointer 1, 2, 3, and 4. So I have done the statement here in VPython, so that's in the green. Pointer 1 is an arrow, and its position vector is the attribute which is the observation position, right? So pos is equal to vector 0, 8 times 10 to the minus 11, 0. I initially defined the axis of the vector as 0. Later on, I assigned that to the magnetic field, and I made them cyan. Now, continuing, what you do is you calculate your displacement vector, which is the observation position vector minus the position vector for your proton. So that would be done as shown here analytically, where you subtract those two vectors, and what you end up with is 4 times 10 to the minus 10 meters, 8 times 10 to the minus 11 meters, 0 for the position vector. So that points in the plus x and the plus y, right? Now, in the code, shown in green, all you do is subtract the position attributes, which are vectors, of the observation, which is the pointer dot pos, minus the proton, minus proton dot pos. And that's how you would calculate your displacement vector in VPython. In the Biot-Savart law, you've got that r squared in the denominator. So analytically, what you do is you sum the squares of the components of your r vector, which is here. If I do that analytically, I get 4 times 10 to the minus 10 meters squared plus 8 times 10 to the minus 11 meters squared. And then when you do that, you get, for your result, 1.66 times 10 to the minus 19 meters squared. In the code, all I would have to do is take the magnitude of the vector r that I defined here, pointer dot pos minus proton dot pos, mag of r, and then square it. Remember that in VPython, to square something, you use the 2 asterisks. You don't use the caret symbol. So that's mag of r star star 2, right? You also need qv cross r hat. You need the unit vector r hat. Now, analytically, you find that by taking the vector r and dividing it by its magnitude, right? So r hat is r over the mag of r. So here, that would be the vector 4 times 10 to the minus 10 meters, 8 times 10 to the minus 11 meters, 0, divided by the square root of 1.66 times 10 to the minus 19 meters squared. Remember, r squared was the square of that vector. You want the magnitude, which is going to be the absolute value of that 1.66 times 10 to the minus 19 square root, right? So if you do that, you're dividing each of the components of the vector by that square root of 1.66 times 10 to the minus 19 meters squared, and you end up with a unit vector of 0.98, 0.2, and 0 when rounded to 2 sig figs. Okay, so that's how you do that. In the code, all you have to do is define a new variable called r hat, or whatever you want to call it, and you can use a few commands, either norm of r, hat of r, or you can calculate it, r hat is equal to r over mag r. Any of those would work, okay? So that's how you do that in VPython. Now, finding a cross product analytically is a little bit of a chore. You can either use a formula or remember that it's the determinant of the 3x3 matrix that's shown here. So if it's v cross r hat, the top row of your matrix is the I hat, j hat, and k hat vector components for each of the 3 cardinal directions. The second row is the components of the velocity vector as shown here, and the third row would be the components of the unit vector. And then you take the determinant of that 3x3 matrix. Now, if you don't remember how to do that, you can look it up. Here, I'm just going to briefly go through it. If you cross out the top row and then the column of interest, so for the I hat component, you cross out the top row, you cross out that first column, and then you take the determinant of the little 2x2 matrix that results. Okay? So if you do that for each one of these cases, then you end up with 0 I hat minus 0 j hat plus, and then the only one that gives you a non-zero component is the k hat. You cross out that third column and top row, you end up with 4 times 10 to the 4 meters per second times 0.2 minus 0 times 0.98. So that gives you 4 times 10 to the 4 times 0.2, which gives you 8 times 10 to the 3 meters per second in the k hat when you do that cross product. Now, that's kind of tedious, as you can see, but in VPython, all you have to do is cross v comma r hat, and you're done. You're in and out. So that's nice. So what you would do then to finish off the calculation is you would plug all of those things in that I just detailed into this equation, mu naught over 4 pi qv cross r hat over r squared. Now note that mu naught over 4 pi, mu naught is the permeability of free space, which in SI units is 4 pi times 10 to the minus 7. If you divide that by 4 pi, you get 1 times 10 to the minus 7 Tesla meters per amps. So that's just plugged into this equation here in the top, 1 times 10 to the minus 7 Tesla meters per amps, times the charge, 1.602 times 10 to the minus 19 coulombs, times v cross r hat, which as we already said is 8 times 10 to the 3 meters per second in the k hat, divided by r squared, which is 1.66 times 10 to the minus 19 meters squared. When you plug all that in, you end up with a magnetic field of 0.00077 Tesla in the k hat direction. Now that gives you the magnetic field at one time step for one observation point. So you can see that it's kind of tedious, right? Kind of involved. If you do that in the code, you just do B is equal to 1 times 10 to the minus 7, 1e minus 7, times the charge attribute of the proton, proton.q, times the cross product, cross v, comma r hat, divided by the magnitude of the vector squared, mag of r star star 2. So that's how you would put it in the code, okay? Now, at this point, I'd like to show you the code and talk about it and run it. So here's the code, chapter 17, problem 60, which I've shared with you and which you're free to copy and use to do your homework. In addition to some of the other things, let's run through this really quickly. You start off to visualize any kind of code from visual import star you call the visual library. Then you define a scale factor. Now this scale factor is because your magnetic field vector is going to be a lot larger in magnitude than your positions. And so you want to multiply it by a small number. This was arrived at a little bit by trial and error, but also by estimating the magnitudes here. So that's my scale factor. Here's that proton definition that I talked about just a minute ago. I define my proton as a red sphere. I put it at its initial position as defined in the problem. I assign it a charge, right? Okay, so all of those things are in there. Here's my velocity vector, v equals vector 40,000, 0. And then I define my observation points. Now there's more observation points asked about in the problem than in the analytical example. In the problem, they want you to look at 4 observation points, which are in the YZ plane around the origin at 8 times 10 to the minus 11 meters from the origin. And so I've defined 4 arrows here, pointers 1, 2, 3, and 4 for each of the observation points. To make my calculation a little less tedious, I created a list of observation points that I call OBS, and I put pointers 1, 2, 3, and 4 in that list. Now, in this problem, I'm going to allow time to move on so that we can look at what happens to the magnetic field as time increases. So I'm going to initialize time, t is equal to 0. I'm going to assign a time step of 1 times 10 to the minus 16 seconds. And then I'm going to let time run from 0 to 2 times 10 to the minus 14 seconds. I arrived at all of these things by doing just a little guesstimation. If you start and end the proton's motion at plus or minus 4 times 10 to the minus 10 meters, and it's going at 40,000 meters per second, and I wanted a few hundred data steps, right? I made it slow so that we could watch what happens, and then here are the steps that I defined. Now, nested within my time while loop, I have a for loop so that I could run through all of my observation points and calculate the magnetic field for each of those observation points, which I do here, and I've already detailed how I went through that. The only other thing that I'd like to bring up in VPython is that for each of my pointers, which are arrows that I've defined here, I go ahead and define an updated version of the axis, right, assigning the axis of my arrow to the magnetic field times the scale factor. And then I increment my time. So it's a simple little short program. So let's run it and watch what happens. So here it is. I've got my proton approaching the origin. It's traveling towards it, and you can see here in blue, you're just starting to see where the arrows are starting to grow. You can see that if you look on, the current is coming the path of that red proton right there, and you can see that the magnetic field encircles, right, my proton according to the right-hand rule. And it is large when the proton is close to the observation points, and the magnitude gets smaller as you move away. So that's what's happening there. Like I said, I did make it slow so that you could see it happen. Right? And you can change that by changing the rate if you want yours to go a little faster. So here it's going, it's getting bigger and bigger, and it's going on through. Okay? So it's just a few lines of code, but it's very powerful and it works pretty quickly, right? And there you can see the magnetic field visualized by the cyan arrows for the moving charge, okay? So it really helps visualize what's going on with magnetic fields. Magnetic fields are a little tougher to visualize than electric fields, I think, inside of your head, because they're at right angles to the motion. And so it's very 3D. And so it's kind of tough to visualize, but you can see that VPython makes it pretty straightforward. So I hope that was useful to you. Remember, you got this code and you can use it to work your homework problems for this week. Let me know if you have any questions, and I'll see you in class.